Okay, this presentation is about cavitation in high energy pumps. Essentially the presentation is focused on pumps, but rather than just talking about pumps on their own, I've decided to make it a little bit more interesting by talking about one particular problem to do with pumps, which is of course cavitation. So I'm just going to pull a few issues together on that. This is all part of the EIT microcourse series, which we do every month. Particular topic of interest. My name is Steve Mackay, and hopefully this topic will be of use to you guys. Briefly, just want to talk about the overview, cavitation, net positive suction head. This is a key factor of a pump, and then some of the factors causing cavitation, and then just a few supplementary pictures. Because we want to try and keep this presentation as short as possible, we won't go through all the slides. But you will have all the slides given to you in a PDF format, so you can review them later at your leisure. So really just briefly looking at pumps, but looking at cavitation, some of the issues there, and my good friend Paresh Gurda has done a lot of the grunt work with the preparation of the materials. He's a high performance expert on pumps and certainly extremely knowledgeable. In fact, he's put together one of IDC's textbooks on vibration management. So cavitation is damage to your pump, typically on the within the pump itself, and we just want to really look at some of the causes of it and to do with pumping. So disturbance that has the potential to increase operating noise levels, and believe me, it can make a huge noise, even in a noisy plant. It can damage the performance of the pump, and obviously cause significant damage to the internals of the pump. Not very difficult to detect. You can actually often hear it. It sounds like sand, gravel passing through a pump. Or if it's fairly severe, it sounds like large boulders going through your pipe work, and the vibration levels can be extremely high. Other aspects you'll see are pressure pulsations, where you'll see the pressure gauge jumping around, and the current ammeter, you'll see that jiggling around as well, and that often is a cause, representation of cavitation. So here's a sort of typical inner guts of the pump. The cavitation regions, as you can see there on the impeller blades, can be quite significant. Basically, when you're pumping liquid, you have a vapor phase formed in a liquid, and essentially we just need to understand what vapor pressure is before we can actually explain what cavitation is. So if you think about a quantity of liquid in a tank, closed container, you get a vapor forming above the liquid, and the pressure exerted by that vapor phase is called the vapor pressure. So if you're looking at pure liquid, the pressure depends only on the temperature. So typical examples of vapor pressure are vapor pressure is 101 kilopascals, 1 atmosphere, 400 degrees Celsius for water. And as you know, at that point the water starts boiling. It's lower for alcohol, ether alcohol, 78.5 degrees Celsius. That's often why you get fractional distillation. So really, when you draw the liquid into the pump, there's often a pressure drop resulting from the fluid friction along the pipeline, valves, fittings, and flow pattern, and you can find that the reduced pressure approaches the vapor pressure of the liquid, and that causes the liquid to vaporize. So you have vapor bubbles forming within the pump pipework, and they travel into the impeller, pressure rises again, the bubbles then collapse or implode, and of course extract tiny bits of metal, as you can see here from the side of the pump. So these bubbles collapse rapidly, and the jets of liquid rush in with high velocity to fill the imploded space where the air was and impinge with energy on the metal. And this can cause severe damage to the internals of the pump. So that's called cavitation. As I say, it can range from very minor pitting to catastrophic failure, and obviously Depends on the pump characteristics, and really a lot of the damage, most of the damage probably occurs on the impeller, the leading face. And you can see a pockmarked rough surface. Here's a few examples. If you look carefully at this diagram here, you should be able to see there's a very major impact on cavitation here, but obviously that will impact on its performance of the pump. Now, to understand cavitation, you need to understand net positive suction head. And as I said, I don't really want to dwell on it too long, but basically, as the pressure of the liquid as it enters the impeller eye has to be greater than the vaporization pressure. This excess head of liquid column is often referred to as NPSH, net positive suction head. And typical example of net positive suction head. Here, for example, suction is your pump, and you can then calculate it through all these additions here: vapor pressure, pipe losses, specific gravity, absolute pressure, and you can then work out the net positive suction head. So again, I'm not going to spend too much time on this. Basically, as the liquid in the suction pipe approaches the impeller eye, you get losses in terms of the liquid head occur due to the velocity and acceleration of the liquid, sharp changes in direction as they enter the impeller, higher flow rates, recirculation due to higher clearance at the wearings. So the above losses are referred to as net positive suction head as required by the pump. So sort of typical, you can get typical curves shown here of Q, which is flow. Don't worry about suction head. When you find you can get Inception, the net positive suction head margin, you always keep a bit of margin between available and required, and typically 1 to 1.5 meters over the entire range of the pipe operation. A few typical numbers here. Typical factors affecting cavitation high energy pumps are liquid properties, hydraulic design, impeller tip speed, blade angle, positive and negative pre-swirls, impeller metallurgy or metallurgy, and operating point and conditions, in other words, the flow rate. There's a formula for estimating impeller life here, which is the loss of material related to the impeller tip speed, cavity length, and time of operation. Again, I'm not going to worry too much about this. Sort of typical areas to avoid cavitation are lower the inlet temperature, increase suction vessel pressure, raise the level of the suction vessel, lower the pump in the pit, replace the pump type with a vertical or submersible type, increase suction line size, remove all redundant valves fittings, and install an inducer to the pump impeller. A few little examples here of pitting and cracking. Porosity of the cross-section, porosity and failed bronze cavitation failure, but particularly bad this one, and very close-up failure there. So as you can see, the actual pitting is quite significant there. And then general corrosion looks like it. So it's actually quite important to distinguish between corrosion and cavitation. So in essence, we just briefly spoke about pumps and one of the major aspects of pumps, which is cavitation. So over to you. Any questions, please drop a line and I'll be only too happy to answer.